In pixel-based graphics, when you zoom into a standard image, you don't reveal more detail. You just get a giant ugly squares of color, as discussed. But now, how vector graphics works to be scaled to size of a billboard without losing a single pixel of crispness. Let's understand practically how Bézier curves help us to define vector graphics. So here, left side you see HTML code, and the right side we have browser, and there we can see the output of this. So for that, we have defined 4 control points: P0, P1, P2 and P3. 3 levels, these are called Lerps. First level Q0, Q1, Q2 along with P0, P1, P2 and P3. Second level R0, R1 but along with Q0, Q1, Q2. Final level, that is third level of Lerp, we have direct image graph along with R0, R1 where time parameter t involved directly. So P1, P2 have gravitational pulls. So especially when P1 and P2 pulls the graph shapes like parabola. So this is how Bézier curve works. If you want points to be defined dynamically at runtime, let's have HTML code and JavaScript. So using this, we can just define the points and accordingly get the different graphs. We are just going live here. So when we go on live, immediately browser opened with the same output, Bézier curves. By the way, please subscribe to Ram Code Logic for more interesting videos and support me. Thank you. So let's now define P0, P1, P2, P3 at runtime. So now I'm defining P0 here, P1 here, P2 here and P3 here like previous one. So the same we can also define the different positions of all these control points. So based on your control points, the graph absorbs the gravitational pulls and accordingly we get the output. The vector files don't store pixels, they store pure mathematical instructions. At the heart of that math lies one of computer graphics' greatest secrets, the Bézier curve. Let's demystify how simple algebra turns straight lines into infinitely scalable curves. To understand curves, we first mastered linear interpolation, commonly known in graphics programming as Lerp. Imagine introducing a time parameter t that moves smoothly from 0 to 1. When t is 0, we are at point P0. When t is 1, we reach point P1. At t is 0.5, we are positioned precisely halfway between both endpoints. This single equation gives us exact coordinates for any point along a straight line segment. Now what happens if we add a third point off to the side? This becomes our control point. The curve won't pass through P1. Instead, P1 exerts a gravitational pull on the line. As t advances, we perform a Lerp on the first segment to find Q0 and on the second to find Q1. Now we connect Q0 and Q1 with a new line and perform a third Lerp along that segment. The path traced out by this moving red dot creates a smooth quadratic Bézier curve. Expanding these nested lerps mathematically gives us a quadratic polynomial in terms of t. Adding a fourth point gives us a cubic Bézier curve, the gold standard of vector design. This requires 3 levels of nested linear interpolations working simultaneously in real time. This exact math behind the pen tool handles in Adobe Illustrator, Figma and CSS animations. The algebraic expression gives us a third-degree Bernstein polynomial. Each term acts as a weight function, determining how strongly each control point pulls the curve at time t. Translating this math into code is remarkably simple and computationally fast. We run a simple loop incrementing t from 0 to 1 in small step sizes. Inside this loop, we calculate exact x and y coordinate values using our polynomial formula. We connect these points with microscopic straight lines. At 100 steps, it appears completely smooth. Because coordinates are calculated dynamically, GPUs render these curves sharp at any screen resolution. Every digital font file on your device uses connected Bézier curves to define glyph shapes. UI designers use cubic Bézier curves to define smooth timing and acceleration in user interface animations. Engineered by Pierre Bézier in the 1960s for car design, this math now powers modern visual computing. Math doesn't just describe our world, it creates the digital interface we interact with every day.